Welcome everyone to today's Rotary Club of Madison online meeting. I hope you're all staying healthy and safe despite the coronavirus threat, whether you're social distancing at home or still working in the community to safeguard others. If you are working on the front lines to protect the rest of us, we can't thank you enough. As you know, we've missed 2 meetings because of the pandemic. It has become clear that we'll not be able to meet in person again for some time. So we've worked out a way to stay in touch and continue our high-quality Rotary programs. And I hope you enjoy this online meeting as a way to stay connected and to learn from an interesting speaker. In this uncertain time, Rotary's 4-way test offers us a guide for how we respond to the information we receive while we take care of ourselves, our families, and our community. Please feel free to join me as I recite the 4-way test of the things we think, say, and do. First, is it the truth? Is it fair to all concerned? Will it build goodwill and better friendships? And will it be beneficial to all concerned? Thank you. And now I'm going to highlight this week's birthday celebrants, who are Jessica Geeson, Bob Grabner, Ron Yankee, Bill Zieneman, and Nick Curran, who shares the following quote. He says, "I've truly missed seeing all the faces of my fellow Rotarians. I hope each of you is doing well and staying safe. I'm certain our club will need to be at the forefront of recovery efforts, and I'm certain we'll succeed in helping our community return to normalcy." Next is Lori Kai and Philip Petrowski, and past President Carol Toussaint, who shares, "Singing 'Until We Meet Again' would seem more appropriate than happy birthday for this April." So she says, best wishes to all as we follow the safer at home order. And then Dick Pearson and Steve Wallman. We wish all of these members a very happy birthday, and we thank those who made a contribution to our Madison Rotary Foundation.
Hi Rotarians, it's Music Committee Chair Casey Oakers, and since we don't have an in-person Rotary meeting today, I still thought it was important that we wish all of our Rotarians a happy birthday. So please join me in wishing all of our Rotarians a happy birthday. Happy birthday and have a great week, everyone.
And now on to this week's speaker. Today we'll hear from Dr. Ankur Desai, who is the Reed Bryson Professor of Climate, People, and Environment in the Department of Atmospheric and Oceanic Sciences and in the Nelson Institute Center for Climatic Research at UW-Madison. His work spans from Wisconsin to around the globe and uses both long-term observations in nature and advanced computer simulations. Dr. Desai will present work both from his lab and from collaborators around the world to show how climate determines weather and how climate change is altering that relationship. So we welcome Dr. Desai, who has titled his speech, "Stormy Days: What Climate Change Means for Your Local Weather."
Hello, everyone at the Rotary Club of Madison. My name is Ankur Desai. I'm a professor of Atmospheric and Oceanic Science at the University of Wisconsin-Madison. And I'm glad you can join me today for this virtual recorded seminar. I'm sorry I can't be there, an opportunity to meet you in person. I hope sometime down the road we'll be able to do that and get a chance to follow up with any discussion you might have. In the meantime, I'm going to share my screens and talk to you about some of the work that I have been doing on climate change. So, stormy days, what climate change means for your local weather. Now, I'm guessing that for many of you, you're not thinking too closely about climate change right now, but it is something that affects all of us and society. And whether that's the snowy scene you saw a slide ago, that was from 2008 in my front yard, and a particularly snowy year in Madison, which is when I started thinking about snow cover and climate, or to the recent fires in Australia, which have devastated 20% of Australia's eucalyptus forests, 5 times greater than any typical fire year for Australia, or even closer to home when we have extreme flooding events, say in southwest Wisconsin or in Milwaukee and Madison, from extreme rainfalls. And you might be curious about whether climate change caused these extreme events. That's a question you might hear in the media and things like that. And I just want to point to you that that's actually the wrong question. It's not an answerable question, actually. A better question is, how much does a changing climate influence the likelihood or magnitude of an event? That's a question that as a scientist I can answer. And what I'd like to do today is talk to you a little bit about some of the work we've been doing looking particularly at winter storms and how the climatic background of snow cover influences the trajectory and intensity of those storms. But to get there, I want to first talk a little bit about climate and climate change. The reason I'm talking about snow in particular is that the climatological seasonal variation of snow in the northern hemisphere is a dramatic and ever-changing event. It's one of the largest changes we see in the northern hemisphere in terms of the amount of energy or light reflected back to space from the Earth. And so I've always been curious, to what extent does that seasonal variability and that annual variability influence things on the planet? And more importantly, how does it influence and how does it change under a changing climate? So what is climate? I like these quotes. Climate is really simply the average of weather, right? And I like this. Climate is what you expect. Weather is what you get, from Andrew John Herbertson from the 19th century, or more recently from Marshall Shepard as a climate scientist. Climate is your personality. Weather is your mood. And I think that's a nice way to think about that. Climate sets the stage for what all of the action that is going to happen. And weather are the things that happen on it, right? Your mood in any one day. And that's something that we'll look at here, particularly with snowstorms. As we'll see later on, climate change is something like a shift in your expectations or your personality, or as I like from a quote from Jason Simonow in the Washington Post, climate change is like what steroids is to baseball and batting averages. And we know that climate change naturally over eons, over millennia, and by humans over timescales of centuries and even faster. So to start with, let's just look at the daily high and low temperature for every day in Madison last year. This is from the State Climatology Office in my building. And what you'll see is some pretty straightforward things, right? You can see in the beginning of the year in February, we had some particularly cold days. And then we can see in summer, it was relatively modest and average and nice, except it was wet. And we also had that cold outbreak again in October. But what's more interesting to me is a climate scientist had a red and the blue lines. The red and the blue are the average from 1981 to 2010 of the high and low for every day in Madison. And they tell you things you might already know. It's cold in winter, it's warm in summer, but they also tell you how much do these deviate from these curves. When somebody in weather forecasting says today was warmer than normal or colder than normal, the normal they mean is the average, these red and blue curves, and how far deviations are these gray lines from those curves. The gray lines are weather, the blue and red lines are climate. And we can also continue this into 2020. In 2020, winter has been a pretty swingy one, where we started warm, then cold, then warm, then cold, and now pretty close to average. I'd ask, okay, well, if I just took all of that blue and red curve and I just averaged it to a single number and I looked at how that changed from one year to the next, I might be able to do that for some weather stations, say throughout southern Wisconsin. And I do that and I get this black curve. The black curve is messy, it jumps up and down, and that's what we call climate variability. Climate naturally varies because of weather being random and chaotic. Some years are warm, some years are cold in southern Wisconsin. There is, underneath that background, what looks like maybe a trend, but maybe you're not so convinced. It's a pretty weak trend if you think about it, from 45 Fahrenheit to about 47 Fahrenheit. But if we start averaging up across space, we start to see some different things. So if we take every weather station in North America, then we start to see some patterns. And so now here the blue and the red are years that are either colder or warmer than average. Here they're using 1950 to 1980 as the average. It doesn't really matter which one you use to get the same answer. But the basic idea here is, yeah, we had this Dust Bowl era in the 1930s that was warm throughout much of the US because of the Pacific Ocean high and land use change. And then we had this interesting period from the 1990s onward where it's very rare to see some blue. At the same time, though, this doesn't really look like the climate change you might have heard about. And one thing that we can do is look at how this varies across space. So this is from the Berkeley Earth Surface Temperature Project, where they looked at global temperature data across the globe and harmonized it into a single map. And the blues here are colder than average, the reds are warmer than average, and you probably notice a few things. One, you might notice that in the tropical Pacific, you kind of come in and out of warm and cold. You might have heard of that. That's called El Nino, or the ENSO cycle. It influences the climate of North America in particular and of South America. You might have noticed that the land masses tend to have greater extremes in reds and blues from year to year than the oceans, and that's because water has a higher heat capacity. It takes longer to heat up, longer to cool down. You might notice that in any one year, you can have places that are much warmer than average. At the same time, other places are much colder than average. And that's just natural variability because of the random organization of climate patterns, weather patterns. But things start to change as you get into the 1980s and into the 1990s. You might notice greater areas of red than blue. You might notice a few heat wave years. You might see that the Arctic in particular is particularly dark red. And here the animation slows down for a few seconds, and you'll notice that all of those patterns seem to be consistent and persistent as we get into the beginning and latter parts of the early 21st century. And that's really what climate change is. It isn't about the weather of your backyard necessarily. It isn't even about the average temperature of an entire country per se, but really how that's operating over the whole globe. And when you start doing that, you start to get into patterns that look like this. So this is the entire world's temperature differences in Celsius. And we've had this roughly 1-ish degrees Celsius increase in temperature since the start of the Industrial Revolution. And here, the 1930s Dust Bowl barely sticks out. You can only, because it was really a regional climate signal, on average, it kind of averaged out. But you can also see that from about the 1980s onward, there has not ever been a globally below average year. And in fact, from the 2000s onward, we have basically almost every year setting a record for warmest year of the globe in the since the beginning of the Industrial Revolution. Here's what 2019 looks like. You can see again that Arctic warmth that's really high. You can also see some cold spots. This one in the North Atlantic is a persistent one. This is actually because we have ice melting off of Greenland into the North Atlantic, and that's keeping that area persistently cooler than it would otherwise. So that's actually consistent with a warming climate. The science of climate change goes way back. And in fact, I like this newspaper article from 1912 in a New Zealand paper that was mentioned by Andrew Rifkin at the New York Times is the one who found it. Coal consumption affects climate. Furnaces of the world burn 2 billion tons of coal a year. Uniting with oxygen, it adds 7 billion tons to CO2 to the atmosphere. Makes the earth a more effective blanket for Earth in raising temperature. This is a remarkably scientifically accurate and short newspaper article, and the only thing wrong with it is the last sentence, which says the effect may be considerable in a few centuries. They underestimated the rate of coal use, but the idea that climate change is controlled by carbon dioxide, which is controlled by fossil fuel emissions, is not new science. In fact, it goes all the way back to the mid-19th century in the work of Joseph Fourier, the father of heat transfer, Tyndall, Eunice Foote. She was one of the first persons to experimentally show CO2 influencing temperature. And so this idea that the sunlight heats the earth and greenhouse gases like CO2 and water in the atmosphere then warm the planet more than it would be just from sunlight alone, at least at the surface, is science has been known for a long time. The idea that CO2 from fossil fuel emissions was the primary driver of change comes from Svante Arrhenius all the way back in 1896. And his main point was that the Industrial Revolution is changing CO2, and a doubling of CO2 may lead to a 3 degrees Celsius warming of climate, or a 4 to 8 degree Fahrenheit change. His number is actually remarkably close to what climate models produce today, even though his math was very primitive. He also wrote that he didn't think there's any way that all the coal in England would ever get burned up in a century, and so that his calculation was really just academic. Little did he know how wrong he was on that point. And finally, for a while, a lot of climate scientists were pretty satisfied that even with CO2 increasing the atmosphere, the oceans would pretty quickly take up all that CO2 as the oceans try to reach equilibrium. And it wasn't until Roger Revelle in some groundbreaking work in field experiments in the 1950s and really demonstrated the so-called buffering effect, that the oceans can only take up a fraction of the CO2 instantaneously, and it takes several millennia for the rest of the CO2 to take up, and at the end, about 2/3 of what we emit will end up in the ocean. And we can kind of test this in computer models where we can actually hold different factors constant and see what drives climate. So here's the observed temperature record in the 20th century and into the 21st. And we can ask, well, how much does changes in Earth's orbit? How much does changes in the strength of the sun? How much do volcanoes, which on average cool climate from aerosol emissions, affect climate? And the short run is they explain some of the variability in climate. We call these the natural factors. But they don't do a very good job of explaining variability in climate from the second half of the 20th century. So you ask, well, what about human factors? And we can start looking at land use. We can look at ozone, air pollution, that is. We can look at aerosols from air pollution, which tend to cool climate, and greenhouse gases like CO2, methane, and N2O, which warm climate. In fact, they more than warm what we observe because they're counteracted by the air pollution effect. And together, the human factors can do a better job of explaining the 1950s onward climate trend. In fact, we have no existing hypothesis for what better explains climate, which is why there is really no debate on what drives climate change anymore. And once you put all those factors together, both natural and human, that's how we understand climate change. We can't predict everything perfectly, but we have a pretty good understanding of how climate changes in response to changes in the Earth system. And as I mentioned, CO2 is to climate what steroids was to baseball. Similarly, we have good measurements of atmospheric CO2. We know it's increasing about 2 parts per million per year. That's actually about half of what you would expect from fossil fuel use, because actually the other half is going into land and into ocean, slowly greening the Earth as well as increasing CO2 in the ocean and slightly acidifying the oceans. We've also have done significant work in looking at paleoclimate records in tree rings and caves and ocean sediments and ice cores. And all of those things pretty much strongly pinpoint a pattern of warming and a linkage of that to greenhouse gases. And the computer models that came out in the 1960s and then really were used in the 1970s for the early scientific assessments and into the 1980s and 90s into the process to develop protocols and policies, you really can't explain 20th century warming without anything other than atmospheric CO2. And this is just a figure showing, for example, we can reconstruct past climates for the past 2,000 years. And, broadly, you can see some patterns like the medieval warm period and little ice age, which allowed for expansions and contractions of civilization, particularly in Europe. But they're actually pretty small changes, like half a degree Celsius. Human civilization for the past 2,000 years has lived in a remarkably stable period of climate. And this remarkably stable period is driven partly by this remarkably stable carbon dioxide concentration, which all changes at the start of the Industrial Revolution. When it comes to policy questions, though, it gets messy fast, right? Because we know already, as most of you know, China's emissions now leads the world. It's the most populous country. That kind of makes sense. But the U.S. has about 4 times higher per capita fossil fuel emissions. And a lot of that has to do with how we produce our energy and where we use it. And so the questions of who should reduce emissions becomes very messy fast. We also know from volunteer science efforts that are done every 4 to 5 years that climate projections, these models that are run, show roughly a 3 degrees Celsius warming in response to a doubling of CO2 with a 1.5 Celsius uncertainty. Most of the remaining uncertainty comes entirely from predicting how much emissions we'll be doing as a result of policy and energy. We also know from both private sector, from federal agencies, from global volunteer reports, from the World Bank, from an influential report from the Department of Defense and elsewhere, that modest warming from 0 to 2 Celsius, remember we've already done 1, creates both winners and losers. Some places actually get a little bit better, a little bit lower heating costs, a little bit longer growing seasons. But it turns out once you get above 2, and especially above 4, you start to see that the negative effects outweigh any benefits. And by 4, you have no real benefits to any part of society. Food security collapses. Invasive species and disease vectors expand in range. Sea level rise floods a lot of major cities of the world. These are the kinds of things that we have to kind of address and figure out if we're trying to figure out how to reduce the impacts of climate change or to reduce climate change itself. And this is kind of the pictorial explanation of that. So here's global carbon emissions over the last 100 years. It's kind of, we're pretty good at keeping track of things we pay for, so we tend to know that pretty well. And one of the challenges here is really predicting what scenario we're on, right? So this is all a function of how rich are we? How many people are there on the planet? What type of energy do they use? Whether there's been any revolutions in policy or technology. And so we have a scenario that is a high emission scenario if we continue to accelerate fossil fuel use, versus one where, say, by the next 20 to 30 to 40 years, we make some rapid changes in our fossil fuel usage, to versus one where we have, within the next 10 years or so, we start implementing some big changes in policy. And the result of that is on the right, which is the change in temperature as a response. And one of the things I like about this curve a lot is that it reminds me a lot of what we're looking at right now with the COVID-19 pandemic. In many ways, you could kind of imagine the slide on the left here is the level of social distancing efforts and policy efforts we place for protecting society and hospitals. And on the right is the outcome or response. And, in the case of coronavirus, there's, a 2 to 3 week or even longer response before the measures we make today have an impact. And the same thing is true in climate, but in a much longer time scale. So now the decisions we make in the next few decades, we won't really tell if they've had an impact until we get out another few more decades beyond that. And that's a real big policy challenge. And it's really interesting to me as a climate scientist right now, seeing how the public health community and epidemiology is responding to and addressing the challenges of social distancing and quarantining and the policies that have to be in place today to be able to so-called flatten the curve, to limit the risks of overwhelming hospitals, as well as to limit the total number of deaths. The same thing is true in climate change in a different way. And I think as climate scientists and climate policymakers, we have a lot to learn from the public health community about how we can better communicate this risk and challenge. So in terms of what I wanted to talk about, this is work I'll present. It's actually done by several folks who worked in my lab. Melissa Breeden, who was a graduate student at the University of Wisconsin Atmospheric Science program. Actually, they also did her undergraduate there, who's now at NOAA in Boulder. Ryan Clare, who's a master's degree student in my lab, who now is working at the Naval Research Lab in California as a meteorological forecaster and modeler. And Matt Ridzik, who is an IT specialist for meteorological models in a private company out in the East Coast, but who also did a master's degree in my lab. So as I mentioned, I'm interested in snow. And one reason we're interested in snow is that if you look at the projections of warming in Wisconsin, because we're far away from oceans and we don't have the strong impact of heat waves and stuff like that, we're mostly seeing a lot of our warming in winter. And this is a projection out to 2050. Winter is about 8 to 9 degrees Fahrenheit warmer than present. And also an extension of the growing season, spring and fall extending out further into season, and summer has the most modest changes. So the changes in winter are interesting to me because what we see across North America from studies done elsewhere is that snow cover, or the existing snow on the ground, is likely to decline everywhere because of that winter warming effect. Not necessarily, say, at high latitudes, but certainly at lower latitudes. And the reason that matters is because snow cover changes the reflectivity of the ground. So we call that albedo. Albedo is just a fancy word for reflectivity. Something that has an albedo of 0 is really dark. It absorbs most of sunlight. Oceans, urban areas like Blacktop have 0% or very low. 100% would be something that's pure bright, reflects everything it sees, so a mirror, or ice. Snow has albedo that can exceed 85%, but is often typically above 2/3. And more importantly, as we'll see in a second, it's the gradient between where snow is and where no snow is. That gradient in winter can exceed 65% difference in where you have snow versus no snow. And this is particularly well noted in the Midwest and Great Plains. So what's shown here is the redder colors are places where when the ground is covered in snow, the albedo is much larger compared to when the ground is not covered in snow. And so what you'll notice is that the Midwest and the Great Plains, because we don't have a lot of trees that block the reflectivity of snow, except in the Great North Woods, we tend to have a really large impact of albedo when snow falls versus when there isn't snow. Now you might ask, why does that matter? Well, it turns out that if you look at one level, it changes temperatures. So here we did this artificial experiment done by a former undergraduate in my lab, Gabe Bromley. And all we did here is we took the Midwest and the upper Midwest, and we've had only put snow in half of it. And we have this line here. And what the colors are showing are places that are cooler and warmer at 2 meters above ground. And I think you have some intuitive feeling for this. Certainly on a wintry day with snow on the ground, it feels a lot colder to you than if there's no snow on the ground. And that's actually what's happening right here. You have colder air north, poleward, where the snow is, and warmer air where you don't have snow. And the reason that matters for weather is because where that no snow line is a great place to create gradients to develop storms. So this is called the Norwegian model of mid-latitude cyclones, goes all the way back to the 1920s. And the basic idea here is that storm systems develop wherever you have these large gradients of warm to cold air. And when you do that, if you have some disturbance in the atmosphere, some chaotic weather-based disturbance that causes some mixing, you'll develop areas of fronts, areas where you have that cold, dense air trying to push that warm, lighter air, causing storms to develop along one side of it. And that mixing and that frontal dynamics, that drives most of the weather patterns we see, particularly in winter in Wisconsin. So my student Matt decided to try to see if that was actually the case. And so what he did was look at the last 40 years of data on snow cover and on storms, and he did a very painstaking analysis of every single snow event that existed over that time over North America, and basically showed that that place where you have no snow, so that's to the south, and places where you do have snow, that's an area of enhanced cyclogenesis, which is a fancy word to saying that's where storms tend to develop and track and intensify. And that's something that weather forecasters have talked about for years, but never really systematically showed, that storms follow the snow line, as they like to say. So we decided to see what's driving that. And so what we did was try to say, well, what happens if the snow line shifted as we might expect in a warming climate? So let's look at this one storm here. January 25th, 1996 was a good snow producer for southern Wisconsin. Here's a picture of NWS La Crosse with like 15 inches of snow from this storm. If we look at a map of where the snow was on the ground before the storm started, so that's what the red is. The red here is showing you that about half of the U.S. was already covered in snow. And the snow storm basically followed that trajectory of where the snow was. And what we wanted to say was, what happens in a changed climate? So the blue here shows that by 2100, if January 25th happened in 2100 in the same exact way, the pre-existing snow cover would actually only be in the blue area instead of the red area. So you can see that southern Wisconsin would not be covered in snow in advance of the storm. This is not saying that every single day in 2100 would be like this, just that we can project based on how much we know snow is likely to retreat in these climate models where we would expect to snow on a single day. Well, we did this for lots and lots of storms, and we did this for lots and lots of different projections of snow cover retreat. And that allowed us to build a database of over 600 different model simulations where we looked at how does changing and reducing the snow on the ground influence the storms and where they go and how strong they are. So the first thing we found was that as you remove snow from the ground, the storms do follow the snow cover. So in any random storm system that comes in will be shifted a little bit poleward or northward in the case of the northern hemisphere, with snow being reduced in North America, especially in the Great Plains and the Midwest. But the effect was really modest. It's about 10 kilometers per 10% reduction in snow cover. So even though the snow cover, as you saw on the last slide, might have been shifted back by about 200 kilometers, in the most extreme example, we really only had about maybe like 40 or 50 kilometers. It didn't quite follow. It can be significant for whether, say, snow hits a major city or not, but it wasn't as big as we thought. There was some other interesting responses, though. What we found was that even though the storms maybe didn't move as much, they did intensify. And so as we had greater and greater snow removal, we had stronger and stronger storms, here measured in the deepening of the central pressure, the low pressure system. How strong does it get? And so we do find that because you have more moisture available under that warmer ground without snow on it, that the storms are able to feed on that and actually grow a little bit more than you would expect. As a consequence of that, what we found was that across North America, on average, if you look at all of the storms summed up together, most of the continent became wetter. A few places got drier, and that's because the storms were shifted a little bit northward, but because they were intense, they dropped more precipitation. The other side, which I don't have here, is that precipitation also was more likely to be rain than snow because you were slightly above freezing in more locations than you were in the original simulations. So as a result, they get wetter and rainier and more intense and slightly northward shifted. And that's basically how this change in climate, the large-scale shift in snow cover, influences any one weather pattern. And this has implications. Rain on frozen ground is a much greater flood risk than snow. Where you have rain versus snow is a major forecasting challenge for major cities and is a major challenge for understanding where the hazards are and where you need to prepare for emergency management. Places that are getting drier may have moisture issues, especially if they're dependent on snow moisture for water supplies. These are all the types of things you can kind of get out of a study like this. And I think it points to kind of the interesting challenge of communicating climate change. Because while the numbers sound small for the average change in climate, a degree here, 2 degrees here, 3 degrees Celsius is still, sounds small, even though that's the difference between the last ice age and present over the last 40,000 years, where we had a mile thick of ice in Madison versus ice limited to the poles. 3 degrees Celsius warming in the other direction brings us closer to the age of the dinosaurs. But from the perspective of weather patterns, what matters not so much is the mean, but also the variability. So what's shown here is the average temperature anomalies in every spot in the world relative to the average temperature. So while the average temperature bounces around because of climate variability and climate change, the spread in that tells you that even under warm climates, you can still have cold extremes. You just have them less often. So we now set 2 record highs for every 1 record low, but you're less likely to have these cold extremes. But you still have them. You still have cold air outbreaks. You still have intense winter storms. They may be occurring in different ways, but you're more likely to have these warm outbreaks. And as you can see, if you know your stats, if a central tendency distribution, this is a Gaussian-ish curve, right, is flattened, that means the tails are extended. So one of the things we're finding is in a warmer climate, we have more extremes, both on the cold and on the warm side, and we'll happen to have more of them on the warm side. That's one of the things that's explaining some of our precipitation patterns we're seeing across Wisconsin. So while winter is kind of getting wetter everywhere, about 20% wetter than it has been in 1950s, on average, what we see in summer is something different, which is only southern Wisconsin is getting wetter. And the reason that seems to be the case is that we're seeing an intensity increase in thunderstorms and convective precipitation. So it's different than the types of storms I was just talking about, but the same basic idea. These stronger storms are feeding on more moisture, allowing us in southern Wisconsin, where you're more likely to be impacted by the Gulf of Mexico and air like that, increasing precipitation. Most of this increase is in 2-inch or more rains, primarily occurring in spring. On the flip side, because you have a faster water cycle, but you don't have as much convection or thunderstorm activity, northern Wisconsin is actually drying out in the summer on average. So finally, to wrap up, this question of, well, what can we do about climate change? And there's really 2 sides to this coin that you have to talk about every time you do this. And the reason for that is because no matter what you do, there's going to be some amount of climate change that you have to address or adapt to, no matter how much you do emissions reductions. So here we are today with our 1 degree of warming. Remember, we talked about 2 degrees of warming is where anything above that, things get worse than they get better. And even if we stabilized and kind of kept constant emissions today, we would still probably not make that 2 degrees Celsius target. And we'd have to adapt some parts of society, especially the vulnerable parts, to dealing with higher amounts of climate change and related impacts on flooding, on sea level, on public health, on invasive species, and so forth. It would take negative emissions, taking CO2 out of the air, increasing the land and ocean carbon uptake to really get us to where we need to be. And this is sorry, I forgot to explain. This x-axis here is the total amount of CO2 emissions since the Industrial Revolution. It takes over a century for CO2 to get out of the atmosphere. So as a result, you can kind of just simply keep track of all of our emissions through all of the Industrial Revolution to understand what climate's going to do. It's actually really simple math when you think about it. So we talk about both adaptation and mitigation, right? So what is adaptation? Adaptation is finding ways to reduce vulnerability or risk to climate change. And this can be economic or political, things like climate migration, for example, of moving people out of flood zone risk areas, or it can be technological, like building seawalls, like having ways to reduce the effects of heat wave and disease, or improving food security under decreased agricultural yield. Here's a great example from the Washington Post. This is the Outer Banks of the Carolina, where already the effect of sea levels influencing flooding during high tides and during storm surges of tropical storms. And so people are building their homes higher. Costs money for sure. Insurance companies are also thinking closely about this one. Closer to home, there's been a lot of work on thinking about how does prairie restoration, how does changing farming practices reduce the amount of runoff and help prevent flooding events from occurring when we do have extreme rainfall. Wetland restoration also has a similar impact. When you get to mitigation, right, it comes down to reducing emissions. And those can be economic, like taxes or cap and trade. They can be regulatory, so things that change how we and where we emit renewable energy portfolio standards. They can be societal in terms of, say, education that reduces fertility rates, that leads to slower population growth. And it could be technological, things that generate and support energy technology and revolutions in how we use energy. And the short answer is there's no silver bullet to emissions reductions. And that's really a message that can be hard to get out as well. Just like there's no single solution to COVID-19, it's really a mix of social isolation and quarantine and testing and vaccines and better ventilators and so forth. The same thing is true with emissions reductions. Any one thing does its piece, but you really have to do all of the above if we want to kind of say cut our emissions in half, as this slide shows. This is called the wedges of climate stabilization. If we focus on electricity and vehicle efficiency and public transport and renewable standards and carbon capture, each one of them doesn't solve the whole problem. But if we do them all at once, and we do them now as opposed to later, you're more likely to be able to get to a state where you might mitigate yourself from the worst effects of climate change on society. And there's lots of great resources out there. Project Drawdown is a group that's been looking at a lot of different policies and technologies and actually very quantifying the cost and benefit of each one of those. And that's helping support investment in some of these. Refrigerant management, which is something you might not even think about, has a strong greenhouse effect. Educating women has a strong impact on societal advances, but also supports population planning better, solar farms, and so forth. The other thing you might say is, well, people aren't going to act because so many people don't believe in climate change. And that's really not true. The folks who are fully dismissive of climate change, this is from a George Mason survey done every year for the last 5-6 years, is a really small percentage of the population, as is the folks who are saying the sky is falling and you better do something, stop everything today. Most people are kind of in this middle category, cautious to concerned. A growing number are alarmed because of some of the extreme events we've seen and the role that climate change is in changing the odds or frequency of those extreme events. And even other surveys, for example, have shown that 75 to 80% of Wisconsin residents support policies on renewable energy, support policies on emissions reductions, on capturing CO2 from coal plants. These are things that we can rally around and get behind. There is actually political will, at least among the population at large, to reduce the effects of climate change through policies that support emissions reductions today. And one thing we know for sure is the youth, this is probably their number one or number two issue on their mind. Youth 18 to 30, generally for you, climate change is one of the biggest impacts on their life and society, and are going to vote in a way that will influence that trajectory into the future. It will be interesting to see. And often when people ask me what's the biggest thing you can do about climate change, my simple answer is talk to each other about it, recognize that you're not the only one concerned about it, recognize that there are ways through political action, through voting, through societal actions that we can actually make a dent and prevent the worst effects of climate change from happening. We can't prevent everything from happening, just like we can't prevent every COVID-19 death, but we can prevent the worst effects. And one of the things I like to end with is this little GIF of eucalyptus growing in a forest. Those Australian bushfires were just last month they ended. It feels like a decade ago right now, but this is eucalyptus seedlings sprouting in that burned forest. The earth will go on. Life will find a way. It's really up to us, though, as humans, to figure out what kind of society do we want to live in, and how does the decisions we make today influence the future of thriving for humanity and for the ecosystems we depend upon. And hopefully, in my little example showing how something as simple as weather can be influenced by climate may make you think a little bit more broadly and deeply about how climate change affects you in your life. And so on that, I'll thank you. Feel free to reach out to me over Twitter or over email if you have any questions. You can also check out my website if you want to see some more details or links to the published papers on this topic. I hope you enjoyed the talk. I hope you are staying safe and healthy, and I look forward to hopefully meeting some of you in the future. Thank you very much.
Well, we thank Dr. Desai for this informative presentation. A reminder to members that you can rewatch this video as well as view past speakers on our club's YouTube channel. You can find the link at the bottom of our homepage of our website, and it's currently showing on your screen. Before we close, I want to encourage all Rotary Club of Madison members in this time of social distancing to stay connected by subscribing to our club blog. You can do so on the members login portion of our website at the link currently shown on the slide. I hope you'll join us again next Wednesday for our online Rotary meeting. Take care, and our meeting is adjourned.